Isomers. So isomers are compounds that have the same formula unit, but a different structure. And because they have a different structure, it affects their physical and chemical properties. So the word isomer comes from the term iso, which means equal, and mer, which means unit. So these are all molecular compounds, and just as a side note, isomers are not allotropes. They have a different word, and so they're different. Allotropes are something that has the same element but have different polyatomic structure. So O2 versus O3, the subscripts are different. Isomers, the subscripts are the same, it's just how I put them together. So we see this a lot in organic chemistry in carbon-containing compounds. So here's an example. C4H10 has two isomers. So I can have my C's all lined up in a row, or I can have three C's here with one branching off here. We oftentimes, when we draw carbon structures, we will just draw the carbons or the nitrogens. We don't draw the hydrogens because it just gets too confusing. Here I've drawn green dashes to show where the hydrogens would be placed, just to show you that there are still 10 hydrogens. But usually we don't even draw that. Sometimes we just draw a line structure in which each vertex is a carbon and the hydrogens are understood. So this would be drawn as this, and this would be drawn as this. Now with isomers, the more parts that you have, the more possible combinations you're going to have. So C4H10 has two isomers. C6H14 has 5 isomers. They can either be a straight line, they can be a straight line with one carbon coming off of this. And notice that if I put this carbon right here instead, it would be the same as this. And I could have two carbons coming off, either off of the same carbon or off of adjacent carbons. So this helps you understand why organic chemistry is its own chemistry, excuse me, because it's a carbon-based model, and the more carbons that you have, the more possible combinations you can have, and the more differences that they have in their intermolecular forces of attraction. So then if we're talking about the isomers and IMFs, we need to look at them in order of strength, right? So these are, again, all covalent bonds. These are all molecules. And so I'm only going to be looking at IMFs within covalent structures. So the most strong intermolecular force of attraction is going to be the hydrogen bond. Remember that the hydrogen bond is a special dipole-dipole. We call it an H bond. And that occurs in parts of a molecule that have H bonded to N, H bonded to O, or H bonded to F. Right below that are regular dipole-dipole interactions between polar ends of a molecule. We write that as capital D/capital D. And again, the more polar the bond, the stronger that dipole-dipole interaction. Then we move to dispersion forces. So high mass dispersion forces, so molecules that are nonpolar but have a high mass, will have a stronger intermolecular force of attraction than low mass dispersion forces. And then when we start talking about isomers, it helps to look at placement. So there's a couple of things. If my polar end, or what we call a moiety, is at the end, it is stronger than if my polar moiety portion is in the middle. And then there's also the shape of the molecule. So if the shape is more linear, it's going to have a stronger force of attraction than if the shape is spherical. So again, this is another way of looking at it. So if I have just looking at isomers of C4H10O, 4 carbons, 10 hydrogens, remember we're not drawing the hydrogens unless they're actually important, and an oxygen. So these are some of the isomers of C4H10. There are actually more isomers than this, but these are the ones that help us illustrate some of the differences. I have basically C4H9 in a line connected to O bonded to H. This is going to have the highest intermolecular force of attraction because I'm looking here at this end is an O bonded to the H, and this is a fairly linear structure right here. Plus this end of the carbon, even though it's nonpolar, I'm concentrating a large amount of the mass of the nonpolar here. If I compare this with the same OH at the end, but this is more spherical right here, the way the carbons are attached, this is going to have a slightly less strong force of attraction because it's harder for these OH ends to interact with other OH ends from other molecules. Then if I have this, where my oxygen is buried in my molecule, then this is going to be even less, because not only is the oxygen-carbon bond less polar, right? It's just a simple dipole-dipole. That polar part is buried in the molecule, and so it's harder to get to. And then even lower than that is where I have a carbon and oxygen bond, and I now have a side to this that is non-spherical. It's kind of branchy. So this will have the lowest boiling point. Now remember that non-polar molecules, and a great example of this is oil, and one of the most polar molecules that you'll be familiar with is water. So see this first molecule, CCCC, connected to OH, which has the highest and most strong intermolecular force of attraction, will have the highest boiling point of all of these isomers listed here. And because it is most polar, it will dissolve best in water. This molecule down here will have the weakest intermolecular forces of attraction because of the types of bonds, where those bonds are located, they're buried in, and the shape, the fact that it's spherical. So this molecule will have the lowest boiling point, and it will dissolve best in oil. So again, this is a way in which molecules that have the same formula, C4H10O, but because they're put together differently, will have different physical and chemical properties attached to it.